This playlist deals with some aspects of Eurocode 2 version 2023. Watch this channel for further selected topics. The video deals with clause 11, detailing of reinforcement, part 3, and in more particular in anchorage of reinforcement. A general picture of an anchorage of straight bars is that you have a control section 1, and on the left hand side it's the anchorage length, and on the other side it's the anchorage force, which is the cross section of the bar multiplied by the tensile stress in the bar. So then you have an equilibrium from the left of section 1 and on the right of section 1. Looking at forces, you can see that when there is compression, when the external force is a compression, then equilibrium can be obtained by the compression field that is developed alongside the anchorage length. In tension, the compression field is in the other direction, but it's in fact exactly the same phenomenon. It's the same principle in compression as in tension. A definition of nominal cover for anchorage lengths is given by CD, it's the design value of the nominal cover, and it is the minimum of half the clear distance of the bars, or it's the cover, the concrete cover in the X direction, the concrete cover in the Y direction, and 3.75 times the diameter. So the minimum of those four values is defined as the nominal cover. It is quite annoying in the formulas that you must take care with the term CS, which is now the clear distance instead of the center to center distance as we are used to. So this is a little bit tricky in the formulas. You have to take care of that. The Eurocode 2 version 2023 gives you a table 11.1, which with a main purpose of making the engineer more easy to apply an anchorage length. So they created a table for certain parameters, and it's a table on the one hand side the diameter, and on the other side it's the concrete quality, and the table gives you the anchorage length divided by the diameter of the bar to be anchored for straight bars. This table is valid for concrete quality between 20 and 60. 60 and higher up, it's not applicable here because for very high strength concrete, the anchorage length is set equal to the one of for FCK equals 60, because they are not sure how the high strength concrete bond, how this will react. So that's why there's a limit on FCK. The table is made for the stress in the bar to be anchored equal to 435 megapascal. So when we are talking about a yield strength of 500 megapascal, then you will see this is the 500 divided by 1.15. You can use this table also for other steel qualities, as long as you know that this table is made for tensile stress equal to 435 megapascal. It's made this table for ribbed bars with a diameter smaller than 32 millimeters. For indented bars, the diameter must be smaller than 14. It's a table for good bond. We will see the definition just now what it means, good bond. When you have a poor bond situation, then you have just to multiply all those numbers here by 1.2, which is easy to apply. It's for tension. You can also use this table for compression, but then you have to subtract from each value here 10. So if you have in compression, for instance, for FCK 30 and a diameter 20, in tension it will be 46 times diameter. In compression, it will be 36 times the diameter. This is made for ultimate limit state, persistent and temporary. And it's made for a clear or for a concrete cover bigger or equal to 1.5 times the diameter. Now, this table is made for CD equals to is equal to 1.5 diameters, not bigger than. Why? Because when CD is bigger than the 1.5 phi, then the values given in the table are safe. But if you have in a real situation CD more than 1.5 times the bar diameter, then you better should calculate the anchorage length because it will save you some steel. Now we can compare this with Eurocode 2 version 2004. And then what we see is that in the version of 2004, the ratio LBD over phi is independent of the diameter. So for each line in the table is the same number as the red ones here on the slide. So this is also already peculiar. In the code version 2023, it's dependent on the diameter, but today, what we are using today, it is not. Also, when you look at FCK 30, then you will see that in the code of 2023, the anchorage length varies from 38 up till 453 times the diameter. But in the version of 2004, it's only 33 times the diameter. So the difference is huge between those numbers and this. So this table 11.1, which is supposed to make your life a little bit easier when calculating anchorage length, is based on the following equation. So I've used the equation of anchorage length and I filled in the different numbers. We will just come to that just now. Then you have this formula, which is LBD divided by the diameter of the bar is equal to this. Phi in millimeters, of course, and FCK in megapascal. And CD is set equal to 1.5 phi. Now, comparing this with Eurocode 2 version 2004 under the same conditions, I recalculate the formula according to Eurocode 2, and I find this relationship with the coefficient alpha 2 equals to 0.925. You see already there's a big difference between the two. And in the dependence of the concrete quality, there is a difference. In the dependence of the diameter, there's a big difference. Now, just take care because CD here is a function of phi. This is a little bit misleading, this coefficient, because there is already a phi disappearing in the factor CD. When we take the ratio of the two, then we see immediately that just this is the ratio. It's less dependent on the concrete quality, but it is rather there is an importance of the diameter here. Now we take some extremes. When you can have a concrete quality of 20 to 50 and you have a diameter 12 and 32, then you see that this ratio, which is valid for table 11.1, varies between 1.09 and 1.76. So the mean ratio in the table, when you recalculate table 11.1 for Eurocode 2 version 2004 under the same conditions, and you take a mean of the whole table, then the mean ratio is 1.4. So it means that you need 40% more anchorage length in the code of 2023. So we can ask now, why is there a mean increase of anchorage length? Why is that so? What changed? And what about existing structures? So does that mean that all existing structures are in danger because they have 40% less anchorage length? I don't know. Now, let's look at the formula to calculate the anchorage length. It's formula 11.3. And yes, indeed, this is more simple formula to apply than it was in the version 2004. This formula, let's look into it in more detail. It is a certain amount in millimeters of anchorage length, and it must always be bigger than 10 times the diameter. The first factor, KLB, is a calibration factor. It is just for the ultimate limit state PNT, it's 50, and for accidental, it's 35. So that's no big problem. KCP is bond conditions. And for those bond conditions, normally we have only two values for it. It's a good bond or a poor bond. But now we have three values, sorry. The KCP is 1 for good bond, 1.2 for poor bond, and 1.4 for instance, a bentonite wall. This formula, it's a little bit tricky. You must take care. This formula is valid for the ratio phi over 20 must be bigger than 0.6. It does not mean that it is valid for a diameter bigger than 20 times 0.6, which is 12 millimeters. That's not the meaning of this. It's the total ratio that should be more than 0.6. So when you got a diameter 10, then this factor is not 10 divided by 20, but it's replaced by 0.6. So this is tricky. Don't forget when you program it in Excel or something else that you should not fall into this trap. The same applies for this ratio, 25 over FCK must be bigger than 0.3. And sigma is equal to 1.5. And we know CD, the factor CD in this formula, we've seen that before, so it's this same thing. Now let's look in this formula a little bit more in detail. According to version 2023, when you look at the different coefficients, then you can say that the anchorage length of straight bars is proportional when all other conditions are equal, are not equal, but are fixed, not changing, then or are constant, then LBD is proportional to the diameter to the power of that's 1.8 or something like that, almost 2. We look now at the formula of version 2004. Then you have the different coefficients. When the coefficients are fixed, are set, then you will see that LBD is proportional to the diameter. So there's a huge difference between the two. Of course, some of the coefficients alpha are also a small function of phi, but that will not change the overall relationship which is here. So we can wonder why. Why is this the case? Is there something that changed profoundly? Well, we can, or there is some explanation for it, and the anchorage length is always proportional to the bond stress and the bond of the steel in the concrete. And in version 2004, we always considered a constant bond stress alongside the steel bar, alongside the anchorage length as a constant one, which is the blue dotted line. But in reality, test shows that there is not the straight line, but it's less in the beginning, it goes up, and then it comes back again. If you look at it in forces, then you will see, okay, we end up with the same force, but in reality, it makes a dip alongside the anchorage length. So that's why the factor comes into the picture. Now, we talked about good and poor bond conditions. Good bond conditions are now defined as bars with an inclination of 45 to 90 degrees to the horizontal. Every bar which is inclined 45 to 90 degrees, so it's almost upright, let's put it this way, then you can say that this is a good bond condition. Or bars with an inclination less than 45 degrees to the horizontal, which are up to 300 millimeters from the bottom of the formwork and at least 300 millimeters from the free surface during concreting. So I added A and B to it. And when you look at this little picture, then you will see condition A is on the left-hand side, which means up to 300 millimeters from the bottom of the formwork. It does not say horizontal, it's the bottom of the formwork. So in this condition, you have 300 millimeters from the bottom of the formwork. So also in this side. So this is still good condition. It's a good bond condition. On the other side, when you have condition B, which is 300 millimeters from the free surface during concreting. So at least 300, that means the green area here indicated here, below the 300 millimeters, that's also a good bond condition. So bear in mind this picture, and then you cannot miss between good bond and poor bond. Poor bond are all the other cases. So that's simple. In presence of confinement reinforcement, the design anchorage length LBD may be reduced by replacing TD by CD confinement. Okay. And when you talk about confinement reinforcement, which is denoted as VC, which is this one, that's the confinement reinforcement. Transfer reinforcement is also a certain confinement reinforcement. Transfer reinforcement is the horizontal bar denoted by VT, transversal reinforcement. And then you can also have an external confinement, which is an applied force sigma CCD that can also play a role in a role in calculating the coefficient CD confined. Just remember that in the formula for anchorage length, CD, the bigger CD, the less anchorage length you need. And CD confinement is always bigger than CD. Now, when you look carefully at this, when you have, for instance, a stirrup, then a stirrup has a horizontal bar and it has a vertical bar. So the vertical bar plays for confinement, the horizontal plays for transverse reinforcement. So in the same bar playing two roles. The question that we can ask now is, when you have a stirrup, sometimes you need additional stirrups, for instance, for shear or for punching or something else. So now the question is this confinement reinforcement and transfer reinforcement in addition to the shear reinforcement you need, or can you use the shear reinforcement as a confinement reinforcement? This is not clear. Why? Because the stress in the confinement reinforcement is not stated or is not given in a formula. Now the CD confinement is the minimum of those four elements plus delta CD, and must always be equal to 6 times the diameter. So by confinement or transfer reinforcement, you cannot gain more than 6 times the diameter in the anchorage length. First question, we'll see delta CD, I'll show it to you just now, is a function of the confinement reinforcement, and this is a function of the transfer reinforcement. Now there's a plus sign. So does that now mean that you can add up the effect of confinement plus the effect of transfer reinforcement? I truly believe so, but it's not clear because this is a plus. So remember this this here, you take the minimum of this, and then you add up delta CD. So this is not clear, but I suppose because it's a plus sign, it's adding into well. The delta CD is given by this formula. It's the bar diameter plus this term. You see the external pressure coming in, and then you have row confinement, and row confinement is a function of the diameter of the confinement reinforcement. So remember, Vc is the diameter of the vertical bar, Vt is the diameter of the horizontal bar. But it can be the same stirrup. Just to be clear, in the confinement reinforcement ratio, Vc is of course not equal to the bar diameter. It's different. It's the diameter of the confinement reinforcement. Just for clarity, I noted I explained the different elements. Phi was the diameter of the bar to be anchored. Vc was the diameter of confinement reinforcement. Vt the diameter of transfer reinforcement. NC is the number of legs of confinement reinforcement. NB is the number of anchored bars. SC is the spacing of confinement reinforcement, and ST is the spacing of transfer reinforcement. It makes it not simple, but let's make an example to make it clear. Let's have an example of transfer reinforcement. You have bars, diameter 20, every 250 millimeters, center to center, and I want to anchor those bars diameter 20. And there is a transfer reinforcement in the other direction, which is diameter 10 every 250 millimeters. And the concrete cover on the transfer reinforcement is 30 millimeters. Now let's calculate delta C confinement. CD is of course the 30 millimeter for this bar, for diameter 20, is a 30 millimeters plus the 10 millimeters here of the transfer reinforcement is 40 millimeters. CD confinement now is the minimum of those three. So you plug in the different numbers and you find the minimum here is 50. This does not count because I stated here 0, but it's not applicable. It's CX, which is not applicable here. So it's a little bit confusing. This should be not on the slide. So it's 50. And the other term was 0 because we only take here into account, for instance, this is for a slab, of course, the transfer reinforcement. So there is no confinement reinforcement. And must be smaller than 120. So CD confinement is 50 millimeters. Now, what is the effect? Well, we know that the anchorage length is proportional when all the rest is constant. It's the square root of 1.5 times phi divided by CD. So that means that the anchorage length with transfer reinforcement in this example divided by the anchorage length without transfer reinforcement is of course the square root of CD divided by CD confinement, and it gives you a gain of, let's say, 10%. So you can gain 10% of anchorage length just by taking into account the transfer reinforcement in this lab. Now, suppose that we are going to increase the transfer reinforcement by diameter 10 every 125 millimeters, then you will see the CD confinement 250 will now change. This 250 will now change in 125. You have CD confinement is 60. You plug it in this formula and you get 20% gain, more or less. So you see the huge importance of calculating the transfer reinforcement, of taking into account the transfer reinforcement. We are calculating the anchorage length. Now let's see when you have an anchorage of a straight bar in compression. That's a straight bar. It's in compression. This is the concrete and this is the soil. Then you need at least a concrete depth of at least 5 times the diameter of the bar to be anchored in compression. And when we have that, then we see that the anchorage length in compression is the anchorage length in tension minus 15 phi. And oh, I said in the beginning of this video it was 10 phi. No, it's 15 phi. Sorry for the mistake. So the total anchorage length for compression is the same as the one for in tension, but you can subtract 15 times the diameter from the length, but you should always be bigger than 10 times the diameter. When we compare this with the version of 2004, then we see in this version that anchorage in compression was bigger than the anchorage length in tension. So now this is a huge difference. In the version 2023, it's less. Version 2004, it's more. So most likely this is because at that time there were not enough data to calculate the anchorage length needed in compression. And when you have less data, you cannot make a very good empirical approach, and you must put yourself on the safe side. So maybe that's the reason. I don't know, but maybe this is the case. Otherwise, it makes no sense at all. Then at last we have the anchorage of straight bars with a diameter bigger than 32 millimeters. To be sure, don't use diameters bigger than 32 millimeters. Never, because it creates a lot of problems. So, but when you have an anchorage of straight bars with diameters bigger than 32 millimeters, then you have to add some confinement and transfer reinforcement. So you see here the vertical bar. Vertical is the confinement reinforcement. The horizontal bar is the transfer reinforcement. And then the amount of reinforcement that you need with a spacing smaller than 5 times the diameter. So this is a very, very small spacing, spacing from 5 diameters. So if you have diameter 10, you only have a spacing of 50 millimeters. Then the vertical bars, the confinement should be more than 0.2 times N2 V squared, and the transfer reinforcement must be bigger than this formula. So this on first sight is different than what we are using in Eurocode 2004 or the version of Eurocode 2 in 2004. But first, the N1 and N2, well, N2 means the layers, and N1 is the bars per layer. So you see here in those two examples, to make it clear, otherwise it's quite complicated, or not clear, let's put it this way. You see here that N2, which is the number of layers, you have only one layer, so N2 is 1, but you have 2 bars in the layer, so N1 is 2. And in this example, you see clearly you have 2 layers, N2 is 2, and you have 2 bars per layer, so N1 is 2. Now, compare it with the Eurocode 2 version 2004, it stays only one formula, which is 0.25 times the reinforcement to be anchored. But looking at this and you rework it, the reinforcement to be anchored is of course N1 times V squared over 4 when the same bar size is used in the same layer of reinforcement. And if you calculate this, you find 0.196 N1 V squared. So this is okay, which is now 0.2, which is normal. So this formula is in fact exactly the same as the one of version 2004.